name is Frank Sanders. I'm the head of the Telecommunications Theory Division at the Institute for Telecommunication Sciences, a laboratory of the National Telecommunications and Information Administration, NTIA, located in Boulder, Colorado. Over the past 30 years, we've developed a series of techniques for measuring emissions from various types of radio emitters. In particular, we've developed techniques for measuring emissions from radar transmitters. In this series of talks, I will begin by describing the fundamentals of RF measurement techniques, and I will culminate the series by describing our techniques for measuring emissions from radar systems, techniques that hopefully you can implement yourself. Accompanying this series of talks are notes available on our website and also NTIA reports that you may find useful. We hope that you will enjoy watching this series of videos as much as we've enjoyed producing them. This is ITS RF Measurement Seminar number 11. Today's talk is Overview of Radar Systems and Technology. This title slide, by the way, shows an advanced radar type called a TPS-59, which is a radar that is carried with an antenna on a trailer, and it rotates mechanically, and while it's rotating mechanically, it scans a beam electronically in elevation. So, here's what we're going to be going through. Whereas in Talk 6 of this series we look quantitatively at the mathematics of radar design, we reviewed the radar equation and we designed our own radar. Now we'll look at the following types of radars more qualitatively. And we're going to try to get through this in 60 minutes, so we do have a lot to cover. But we're going to follow radars basically here in this talk as a function of their missions and their design types. You can tell from the length of the list that there are a lot of different types of radars in the world. One thing before we really get going, in radar design and radar operations, the word target is used a lot. Here, in this context, targets means anything that a radar is trying to observe. The term probably stems from the development of radars in the Second World War for warfighting applications, but nowadays target doesn't necessarily have anything to do with any military applications or functions. Even if you had somebody in the water and you were trying to rescue them and you were following them with some kind of a radar, you'd still call the person a target from a radar design standpoint. I'd like to do just a brief historical introduction because I think it's good to know where we've been in terms of where we are and where we're going with radar designs. Shortly after radio technology got developed for communications in the early 20th century, various researchers in the US, Germany, and Britain noted that when ships were passing up some narrow channels, the ships would disturb radio propagation between radios that were trying to operate across the channels. And at the time, people were really worried about how they could detect aircraft at long distances. Air forces were being developed, and there were people who were writing long exposés about how air forces could and would be used to destroy population centers. So the idea was to be able to pick up aircraft at long distances. Initially, people tried to do it with acoustic systems. There are photographs in existence today that show people sitting in chairs with giant horns stuck in their ears, and they would rotate the person in the chair with the giant horns turning around and around and around, kind of like a radar, trying to listen for aircraft at long distances. That didn't work out so well. But these early observations about the disturbance of radio propagation bore more fruit. And so by the late 1930s, early 1940s, radio detection and ranging, so-called radar systems, came into existence. The word actually appears in print for the first time in 1941. As it turned out, radar was the key in many respects to winning the Second World War for the Allies because early in the war, in 1940, after France had fallen in June of that year, the war having started in September of 1939, the British were facing the German armed forces alone, and they were facing an invasion of their island. We now know that had Britain been invaded, we wouldn't have had a giant aircraft carrier from which we could launch the Normandy landings later on in 1944. So what the British needed to do was defend themselves. They needed to prevent a landing from occurring in the island. To prevent the landing, they had to prevent the Germans from getting air superiority. That meant that they had to beat back the Luftwaffe. And the Royal Air Force had a big problem, which was that there were not a lot of planes in the Royal Air Force. They didn't have a lot of gasoline available, and you could wear pilots out really, really fast if you tried to just put aircraft up in the air and maintain standing patrols 24 hours a day, flying back and forth, looking aimlessly and randomly for incoming German aircraft. Luckily, British
scientists and engineers had developed a radar system called chain home, and they had built it before the war had begun. The chain home system allowed them to see German aircraft coming when they were still on the eastern side of the channel, and it allowed the British to selectively apply their air power in a very efficient manner. They could wait until the last minute to get their aircraft up off the ground, and then they had radio voice controllers who would talk to the pilots and tell the pilots what direction to go to find the German aircraft based on the incoming signals from the chain home system. And because they didn't have to maintain costly and really non-sustainable standing air patrols, it allowed them to win the Battle of Britain, and as I say, ultimately led to the...
It was a low-frequency system, what, around 30 megahertz?
30 megahertz are a little higher. Yeah. The radars were transmitter antennas on giant towers. They didn't have any moving parts, but they were able to use them in such a way that they could actually triangulate on the echo returns. We kind of discovered the problem of maintaining standing air patrols after 9/11 because there were various times and places where the U.S. government tried to maintain standing air patrols, and it didn't take them long to wear out the aircraft and the pilots, and they're terribly expensive. So really, you do need radar systems for early warning. Now, to continue the history, and Bob, you commented that the chain home system was basically operating at rather, by today's standards, rather low frequencies. The goal was ultimately to be able to put aircraft and ships out into operational scenarios where they're carrying radars. And in order to do that, you needed to have reasonably small, compact radar antennas. And in order to do that, you had to operate at rather high frequencies, because remember that the whole key to radar is to form a directional beam. If you're going to form a directional beam, you have to build an antenna that's substantially larger in diameter than the wavelength that you're trying to form with the beam. And if the antenna has to be fairly small, then the wavelength has to be even smaller, which means you have to work at pretty high frequencies. As it turns out, you have to work at microwave frequencies. British scientists made a breakthrough. They developed a tube called the magnetron that can convert line power, 60 cycle or 400 cycle power, into microwave energy. And they carried the prototype magnetron across the Atlantic on a ship. They arrived in Massachusetts. They showed it to people, as I recall, at the MIT Lincoln Labs, and basically the people at Lincoln Labs said, this is what we've been trying to do. Now, although the British had developed the conceptual breakthrough on the design of the magnetron, it took American manufacturing capacity to produce thousands of magnetron, and therefore, because magnetrons work at microwave frequencies, microwave radars that were used by all Allied forces around the world. They were used on land, they were used in aircraft, they were used at sea. They played key roles in every major campaign. The Axis powers did develop radars, but the Allies arguably, I think, put them to better use. For one thing, because this manufacturing capacity that the United States had just allowed enormous numbers to be built. One in particular that I'll mention later was the advent of precision approach radars. About 20 years ago, I heard a talk by Luis Alvarez, who is an American physicist who was one of the designers of precision approach radars, and he talked about how they developed these at MIT Lincoln Lab during the Second World War. They had a particular problem, which was that aircraft were coming back from missions in Europe to England, and they were trying to land in completely socked-in conditions, fog, rain, darkness. You couldn't find the airfield at all, and if you could find the airfield, you still couldn't get yourself on a glide slope and get lined up and make a safe landing. The development of precision approach radars that we'll talk about later saved thousands of aviators' lives during the war, and again made a significant contribution. Now, after the war, the advent of the Cold War meant that early warning and alert systems were still extremely critical, and so radar development and design progressed rapidly in the years after the Second World War, during the Cold War. Coming pretty much up to the present, radars are still being designed and developed, but they are very costly to design and develop nowadays. So there are a lot of legacy radar systems that will be around for decades to come. And it's not a trivial matter from a programmatic and a financial standpoint to say you're going to develop new radar systems. Looking at today's radar technology, we still have tube-type radars in existence. These are radars that use magnetrons, klystrons, traveling wave tubes, etc. And these have been around for over half a century. They're still very popular. In the last roughly 20 years, solid-state radar transmitters have become very popular. Now, solid-state radars do offer advantages over tube-type radars in terms of cost and maintainability. Interestingly, though, and this is kind of a reversal of the usual paradigm between solid state and tube systems, solid state radars are typically heavier than tube radars, and they cannot develop the high peak power levels that tube radars can design. That results in some interesting trade-offs when we consider the problem of picking either a tube or a solid state system for a radar transmitter, and we'll talk about that in the course of the next 3 slides, because this affects the choices that designers make for all the radars that we'll see through the rest of this talk. Now, first of all, let's look at what happens if you have a radar running with a classical high-power tube, and we'll consider the case of a radar like we talked about in talk number 6, where it's a radar that's going to operate at maybe 100 nautical mile range to detect and track to detect and track aircraft out of those distances. So a radar like this typically is operating with about a 1 microsecond pulse width, and then it listens for 1 millisecond, 1,000 times longer, and then it switches back to the transmitter and fires out another 1 microsecond pulse. And the echoes that come back into the radar receiver between the transmitted pulses are typically at levels that are actually below the radar's noise level, but when we integrate 15 or 20 echo returns from 15 to 20 separate transmitted pulses, we can basically integrate a target up to a high enough level to actually be able to declare it as a target on a planned position indicator, classic radar display. So radars are always fighting against their internal noise. Now, I mentioned a second ago that solid state radars can't generate the high peak power that the tube type radars can. Typically a solid state radar is generating about 1/10 as much power. But we still need to get the same amount of energy, total energy, into the radar pulse with a solid-state radar as we would with a tube-type radar. So if the power level is 1/10 as high, the length of the pulse needs to be about 10 times longer. This means instead of being maybe 1 microsecond for this type of radar design, we're now up to a 10 microsecond pulse width. So this radar has a higher duty cycle than the tube-type radar does, duty cycle being the pulse width divided by the pulse repetition interval. And this has serious implications for being able to resolve the range of a target, because if we simply transmit a plain vanilla sine wave inside this pulse, we can't resolve the target location to anything better than about half of 10 microseconds, which is 5 microseconds, which is 5,000 feet, which is a mile. So we'd have a 1 mile kind of uncertainty in terms of where the target is. We don't want that. We want the uncertainty in target distance to be more like 500 feet, which is what we can get with a 1 microsecond pulse. So what do we have to do? Something has to be done. What we do is we put coding into the pulse. There are only 2 waveform parameters that we can modulate other than amplitude, and that is either frequency or phase. If we modulate frequency, we can turn on the pulse at time 0, run the pulse up for, say, 10 microseconds, but while the pulse is running, we change the frequency of the pulse. We've got frequency changing on this axis. Now you can have a downward running frequency change. We can have an upward running frequency change. This is called chirping. And if you listen to these, you actually do hear something that sounds like a bird's chirp if you play these out at audio frequencies. And when these pulses are received, they pass into a set of frequency-dependent delays inside the receiver, which actually compress the pulse in the receiver down to, say, a 1 microsecond pulse width, and now we get our range resolution back. The other parameter that we can modulate is phase. Now, a mathematician named Barker designed a 13-chip algorithm in which phase is varied from 0 to pi, and we can represent these values of 0 and pi in phase within the pulse, which again is going from 0 to 10 microseconds, as being, for example, 1 0 1 1 1 0 1 0 0 0 0 1 0, etc. And these can likewise be used inside the receiver to resolve the pulse down to the length of 1 so-called phase chip. It's also true that we can use minimum shift keying rather than discrete 0 to pi transitions. Either way, we code the pulse with phase, and we can then use pulse compression techniques in the receiver to get a compressed pulse and therefore a high-resolution output. Now, if you ever want to see these characteristics of either phase modulation or frequency modulation in transmitted radar pulses, vector signal analyzers are an excellent choice. There are some other tricks that exist for seeing that, but I'm not going to go into it in this talk. So with that said, just be aware that you can pick tubes for radar design, you can pick solid state, but there are trade-offs, and unlike other parts of the electronics world, solid state designs in radar are not necessarily superior to tube designs for various applications. Now, a question that comes up both in the United States and also in the ITUR is, are radars still needed in a world of precision satellite positioning? We now have 4 systems that are either online or coming online: GPS, GLONASS, Galileo, Compass. The question is asked, so if you've got all these positioning systems, why do you need radars? Well, the reason is basically that radars can track natural phenomena, and they can track discrete targets like aircraft and ships, which are non-cooperative, which are not themselves beacon equipped, which are not trying to be seen or found. They're also, of course, ideal for seeing coastlines. They're ideal for seeing vehicles and people moving across terrestrial surfaces if you're up in an aircraft looking down on them. They're ideal for monitoring ocean surface conditions. So although in some cases beacon systems on appropriately equipped aircraft can and do provide excellent location information, we believe that radars will continue to be needed for the foreseeable future because of safety of life and national security needs that really cannot be met in any other way for, as I say, non-cooperative targets and natural phenomena. Okay, so with that as an introduction, let's move on to radar types and descriptions. This is, by the way, a giant radar in a 10-story building called PAVE-PAWS. PAVE was a program name, and PAWS means Phased Array Warning System, big electronically steered radar. We'll see more about it later, too. Okay, we'll start off with HF radars. These are used for observing airborne, so-called air-breathing targets, and also for performing maritime surveillance missions where they're looking at ships and boats on the ocean surface. They can even see periscopes that are poking up out of the water. The U.S. HF radar band is 5 to 28 megahertz. HF radars are really neat because they don't cost very much money, and as we'll see in a moment, they provide extremely wide area surveillance of both airspace and oceans at distances of thousands of miles from a nation's territory. Countries with long coastlines such as the United States and Australia are able to really take advantage of this type of technology. Now, unlike most, pretty much any other radar types, HF radars use ionospheric propagation to get energy way out over the horizon and backscatter it from targets, and these are called OTHB systems. And this means that they don't just get line of sight coverage, which is what all the other types of radars we're going to look at today do get. The U.S. Navy and NOAA operate HF radars. The Air Force has had them operating in the past. They might have them again in the future. They're good. HF radars are excellent for looking at small aircraft and boats. They can then provide interdiction information if they think that an aircraft or boat is something that they need to take a closer look at. They're terrific for looking at sea surface conditions over large areas. And unlike other types of radars, they don't operate with pulsed emissions. They actually transmit carrier waves. So they're basically 100% duty cycle transmitters. Key things about HF radars is that they are low cost as an alternative to space surveillance, which is very difficult, very costly, and they can give you continuous coverage over a given area.
And we all remember the famous Russian woodpecker radar
Right.
in the 1980s.
Amateur, Bob mentioned the Russian woodpecker. Amateur radio operators used to hear a Russian type of radar, HF radar, that they called the woodpecker because it sounded on an HF radio like a woodpecker running, yeah. Mm-hmm. Here's a diagram that shows basically how an HF radar would work. You have a transmitter location that's located on land, on shore, and actually the receiver is not co-located. The receiver is typically 100 or 200 miles away, but at this kind of scale, that's an insignificant distance. So technically they're bistatic, but they work almost like a monostatic radar. They don't work over the Earth's poles. Ionosphere does not support propagation that they need over polar regions. So in polar regions, we still need the distant early warning line, which consists of long-range microwave-type radars along here. But over the oceans, what happens is this carrier wave energy is transmitted out. It's directed electronically out of the radar. It is bent and refracted through the Earth's ionosphere. It hits the sea surface out here, and they have these little feet that they run sequentially, 1, 2, 3, 4, and so forth in these sectors. They get the backscatter information back, and as I say, they can see sea surface conditions, they can see boats' wakes, they can see boats, they can see ships, they can see periscope wakes, they can see air-breathing threats. Even if someone is skimming along the surface 5 or 10 or 20 feet above the water, they can see them moving in. And the distances, as you can see here, are really enormous, give or take 1,000 miles out from shore for not a lot of cost. This is the coverage from two HF radars, one that's on the North Carolina-Virginia state line, another one that's in Texas, that look out over the Caribbean and into the north part of South America. And again, they can use this to look for targets of interest and guide interdiction through this area if they need to. Notice that HF radars do not give you coverage right in close to the radar. That's because you're propagating the energy up into the ionosphere. So you can see things really far away. You can't actually see something in really close. If you want to see something in close here, you'd have to use a microwave radar. Schematic coverage that NOAA has provided for how they haven't done this yet, but how they would build radars that could observe sea surface conditions over very large areas. NOAA does operate some HF radars right now, but they don't have this much range. Some pictures. This is the deactivated over-the-horizon backscatter radar that the Air Force used to have. I think this is the site up in Maine, and this is the so-called relocatable over-the-horizon radar that the U.S. Navy operates, the so-called Rother. Truth be told, they're probably not all that relocatable. Now move on to line-of-sight coverage radars. These are your classic radars. These are the ones that you see in movies. These are the ones that we talked about in talk number 6. They typically operate at frequencies of a few hundred megahertz or above. The lowest frequency U.S. radar band I can that I'm aware of was at 200 megahertz. It no longer exists. Nowadays, our lowest frequency band is 420, 450. These are so-called UHF radars. If a radar operates above 1 gigahertz, then it's a microwave radar. Now, line-of-sight coverage, as we'll see in a moment, is limited by both terrain shadowing and also by the curvature of the Earth. And in one of the earlier talks in my series, I derived this equation for the range that you can see out as a function of height above the Earth's surface. And if the range is in nautical miles and the height is in feet, then the formula is 1.2 times the square root of the height in feet. If you use this, you find out that at a distance of about 225 nautical miles, if you're looking out at a tangent to the Earth's surface, if you look out horizontally from the Earth's surface on the Great Plains of Colorado or Texas, or you're out on the ocean somewhere, then at a distance 225 nautical miles out, your line of sight along your surface is 35,000 feet high, and there's not a lot of stuff flying above 35,000 feet. There are some things, but not a lot. So this kind of limits the usefulness of line of sight radars. We will talk about airborne early warning radars that actually are somewhat of an exception to that rule. Here's a schematic diagram. Here we have a radar station that's located on land or on a ship on the ocean. Another radar station. In both cases, the lower edge of their beam is basically parallel to the Earth's surface. And I've drawn these such that their coverage at 225 nautical miles out, let's say, is just touching. But at this altitude, they can't see anything that's basically below about 35,000 feet out here. So this is what people mean when they talk about flying under the radar. If you're moving along in this zone in here, these microwave radars that are line-of-sight systems are not going to be able to see you. I've exaggerated the geometry in this diagram just to demonstrate this. This also means if you see a circle on a map and someone says, "Ooh, here's a radar and it's got a 200 nautical mile range coverage," and so they draw a circle that's got a radius of 200 nautical miles. Remember, what they're doing is they're drawing a circle that has that for a radius, but remember that out toward the edge of that radius, they can't see very much. Not because the radar isn't sensitive, but because most of the targets that they're looking for in an air surveillance system are down below that level. So just keep that in mind as we move on through the talk. Okay, so having said that, short-range air surveillance radars look for airborne targets at ranges out to about 100 nautical miles, so about half of 225. And they always have target processing capabilities for tracking these targets. Often they operate between 2,700 to 3,700 megahertz. That's a nice frequency band for this kind of application. Again, remember that they're limited by line-of-sight coverage, terrain shadowing. Vertically, they can see from typically about a half degree above the horizon to 30 degrees above the horizon. They can resolve a target in azimuth down to about a half a degree, and the range resolution is typically on the order of 500 feet, so about a tenth of a mile range resolution. They can update a target position about every 5 seconds because that's the rate at which they're rotating and scanning. They do not generally get altitude information out of these radars, and so beacon interrogator systems, which derived out of the old World War II identification friend or foe IFF systems, and still sometimes called IFF, are used to get positive identification of cooperative airborne targets, and also to get the altitudes of those targets as read from the target aircraft through an encoding altimeter inside the aircraft with the beacon interrogating the plane at 1030 megahertz and replies at 1090. In other words, a lot of air traffic control is really done with this air traffic control beacon interrogator system. But with that said, if that system fails or someone turns it off or someone's flying without the interrogator system, then you can always go back to the primary radar and at least get distance and azimuth. These radars do operate with pulsed emissions, typically about a 1 microsecond pulse width, 1,000 pulses per second, a megawatt peak power coming out of the transmitter, and that means 1 gigawatt EIRP, a billion watts EIRP coming out of the antenna, because the antenna typically has a little over, in fact, a little more than 30 dB of gain. Now, the new solid-state transmitters, remember, have longer pulses and lower peak power levels, and that necessitates pulse modulation techniques if you go to a solid-state design. The numbers I just gave you there in that bullet are for classical tube-type radars. These types of radars are often used for air traffic control at airports. They're called ASRs, Airport Surveillance Radars. Models in use in this country right now are the ASR-8, the ASR-9, both of which are tube-type radars with klystrons, and the ASR-11, which is a solid-state radar. Shipborne versions are used for naval air traffic control, and there are mobile tactical versions of these types of radars that can be deployed on locations or at locations around the world. Because the antenna beams on these are usually vertical fans, remember, you generally don't get elevation angle data, and therefore you don't generally get target altitude data. Or in some cases you get some minimal information. So it is important, if you've got cooperative targets, to get them to operate with beacons. Otherwise you have to take other measures to try to get altitudes. Typical ASR, this is the feed where pulses are fed out. This is the reflector that forms the beam. Echo information comes back into this and then is focused back down on the feed. There are two feeds on this, and it does form two beams vertically, so it's got a little bit of elevation discrimination, but not a lot. This is the beacon antenna up on top. It spins with the radar antenna, but electronically it's a completely separate system. This is transmitting interrogations at 1030 megahertz and getting the automated replies back from the aircraft at 1090 megahertz. You can mount the beacon completely independent of the radar if you want to. In fact, if you got to get a cheap system up and running fast, you can set up a beacon all by itself with no radar. This is the profile, just shows you the parabolic cross-section of the radar reflector, shows you the two feeds forming the two vertical beams, and then the beacon antenna, which is a little phased array. In order to avoid clutter from low-lying objects near the radar, like this kind of stuff and trees, they will often put these radars up on fairly high towers, 80 feet high, for example, to get them up out of the nearby clutter. That's a scale picture. They told me it was turned off when I got on it, so...
Did it feel warm?
Yeah, but they said it's just a warm day, don't worry about it. And
medicinal.
yeah, medicinal. And this is a picture of the vertical fan beam coverage for this type of a radar. You've got the lower fan beam and the upper fan beam, so you get a little bit of elevation information, but not much with these types of radars. This is a TPS-78 built by Northrop Grumman. It's a kind of a medium-range tactical air search radar, the kind of thing that could be set up by armed forces on short notice. The antenna rotates mechanically, but can do, if I recall correctly about this antenna, can do some vertical beam scanning and get some 3D information by scanning electronically in elevation while it's rotating. Then you've got a little operator trailer here, you've got a power supply trailer, and so forth.
Nicely labeled.
And these things, right, and these things can typically be, it is nice advertising, and they can typically be loaded into aircraft and shipped on C-130s or C-141s, C-5s. Long-range air surveillance radars are similar to the short-range air surveillance units. The difference is that they operate out to typically 200 to 225 nautical miles. A popular frequency band for these radars is 1200 to 1400 megahertz, largely, but not entirely, because atmospheric propagation in this frequency range is really excellent for long-range radar operations. Again, their line-of-sight coverage, we've already talked about how earth curvature and also terrain shadowing, that is due to mountain ranges, hills, etc., can shield or shadow the radar coverage. Vertical coverage, again, goes from about half a degree to 30 degrees above the horizon, so there's actually a cone of silence or a cone of darkness directly above the radar where it can't see anything. Azimuth resolution, again, typically half a degree, and I've seen it sometimes up to 1 to 1.5 degrees azimuth resolution. Longer pulses, typically 1,500 foot range resolution, but it's not as critical to get the tight range resolution because these radars are operating at longer ranges to begin with. Scan updates are every 10 seconds. Because they have a lower pulse repetition rate, because they have to work out to double the range, but they still have to get 15 to 20 pulse echoes back to integrate a good return on a target, they have to slow down the radar rotation so that it moves slowly enough to wait for the energy to get out to the longer ranges, hit a target, and echo back. So the scan updates for long-range radar are every 10 seconds, whereas for short-range radar, they're every 5 seconds. So if it's a tactical situation, that could be a bit of a problem, but that's the trade-off you face if you're going to work out to longer ranges. Again, it's important that these radars typically be augmented with beacon interrogator IFF systems for all the cooperative targets in a given area. By the way, one of the reasons for IFF is not just so you can spot or try to get some assistance with spotting bad guys who either are not responding to the beacon at all and are being seen by the radar, or who can't come back with the right codes, but also so that if you see a response back from an interrogation and the response says, "Hey, I'm a friendly person," you don't accidentally shoot at them. Pilots really appreciate that feature, especially with the new air defense systems that basically really don't miss anymore, movie scenes notwithstanding. So typically, these pulsed emissions are 3 to 10 microseconds. They're longer pulses, lower pulse repetition rates because of the longer ranges, but still for the tube-type radars, a megawatt peak power out of the transmitter, over a gigawatt actually of EIRP coming out. And again, there are solid-state systems that are in operation. They transmit the longer pulses at the lower peak power, and again, they have to use those pulse modulation techniques in order to get the range resolution back. The ones that are used for air traffic control and also are used for air surveillance of incoming aircraft from outside the United States along the national periphery are called Air Route Surveillance Radars, ARSRs, ARSRs. Nowadays, ARSR data feeds are sent to NORAD, the North American Aerospace Defense Command. They're sent to the Department of Homeland Security, and they're also sent to FAA Air Traffic Control. So these are used to watch aircraft at long distances, typically on high altitude routes up at 25, 30, 35, 40, 45,000 feet. The ARSR 1s and 2s basically date back to the Second World War in terms of the basic technology, although they've upgraded the receiver electronics over the years. The ARSR 3 is a beautiful tube radar design, and the ARSR 4 is a solid-state radar design. There's a new type, which I misspelled, coming. It's the common. Not common, I'll correct that. The common ARSR, the CARSR, which will be an upgraded version of the ARSR 1s, 2s, and 3s, and it'll be solid state. And they're in the process of building that right now. Naval versions of these radars are used for long-range naval air surveillance, and there are mobile tactical versions of these kinds of radars that can be deployed to support air operations over land masses pretty much anywhere in the world. The older types just use simple vertical fan beams for their coverage. The newer types often, like the ARSR 4, for example, the ARSR 4 have stacked vertical beams that give you some elevation information. Again, beacon systems are important. The only other way with these radars to really get elevation information is to put a second radar in the vicinity of the ARSR, and it's called a height finder radar. And a height finder radar looks like an ARSR turned on its side. And it nods up and down, and it gets the height on a target, but you have to select the azimuths on your targets one by one by one. It doesn't get 360 coverage. I'll explain a little more in a second. So here's an old style, but still currently used type of reflector for a long-range fan beam type air surveillance radar. This is one that would be rotating around mechanically every 10 seconds. You wouldn't get any elevation information, but there is a height finder version of this radar where they turn this radar antenna 90 degrees, and then when they see a target of interest somewhere, they have to move the height finder antenna to the azimuth where this radar saw the target, and then they nod the antenna, the height finder antenna, up and down, up and down, up and down, up and down, and they get the elevation that way. It's a little bit antiquated and a little bit slow, but again, if you're going to do it with any precision, that's the classical way of doing it. This is a long-range air search station for an Air Force radar. These kinds of stations are on the distant early warning line up in northern Canada. Remember that HF diagram that I showed you that showed the microwave radars? This is the sort of radar that's up there in northern Canada, and these radars have been designed and built to operate completely autonomously, completely remotely, with no people present. They come up once or twice a year to service a generator and refuel it with diesel fuel, but they don't have to keep people up at the station.
What's this location here?
This is at Hill Air Force Base in Utah.
Okay.
Yeah, nothing classified about that, nothing secret. It's perfectly, out in the open. This is the TPS-59. I mentioned that a minute ago. Now, this is a 3D radar. It rotates mechanically about once every 10 or once every 12 seconds, but while it rotates, it scans a beam vertically, electronically like this, and it gets elevation angle information while it's rotating around. So it's a combination mechanical and electronically scanned radar system. TPS-59. This is an FPS-117. This is the kind of radar that is operated up on the dew line, and again, mechanically rotated with an electronically scanned beam to get some elevation information out. So a 3D radar that's a combination of mechanical and electronic scanning. Notice the little beacon antenna up there on top. See, the beacon's still important. There's a side view. This is fed by a set of amplifiers on each row, and they phase the amplifiers one to the next to get a vertical scanning characteristic or behavior out of the beam while it's rotating. And of course, it forms the receive beam the same way. This is the antenna of the Arcer 4. Look at the size of this thing compared to the size of the people inside. And this antenna is so finely balanced that if you just give it just a little tap with your hand, it'll start rotating. It's that beautifully balanced. People have been known to ride on it, I'm told.
Kind of fun.
This is the feed out in front of the Arcer 4. Remember I said it's a solid-state radar? This is the feed, and the feed consists of a set of solid-state modules. This is why, in a certain sense, solid-state radars are heavier than tube-type radars. You have to put so many modules in. Each of these modules is, I don't remember exactly, it's 1 watt, maybe 5 watts per module. So you have to put a huge, huge number of these modules together in order to get any kind of a high peak power level. And the peak power level is still 1/10 of what a tube would produce. So what they've done, in effect, is build the transmitter with all these modules right out here on the feed in front of the radar reflector. Again, when they get the echoes back, it operates reciprocally. And here, to save space, they've actually put the beacon antenna in front of the feed, like so, instead of putting it up on top of the main reflector. So there's another view of the solid state feed. I'd like to point out, and I think I mentioned this in Talk 6, that every radar is designed by somebody who had a vision for what they wanted to do and wanted to create a sort of electronic form of art. They want to solve a problem, and they want to do it like no one's ever done it before. It's a sort of a form, I think, of electronic sculpting. They're not really cookie cutter systems in terms of design. Every radar design, every type of radar model is handcrafted and hand built, and represents the designer's attempts to make a lot of trade-offs to try to get some optimal design. And of course, there is no perfect radar design. There's no such thing as an completely optimal radar design in every sense. Now, having looked at the various types of terrestrial, short-range, long-range microwave radars, we'll look at airborne, long-range early warning, and air traffic control radars. These are called AWACS, generically, airborne warning and control. And by control, they mean air traffic control. But if you try to make that into an acronym, it's horrible, so they just go with AWACS. These are mounted on aircraft, and they can watch other targets that are up in the air, targets on the ground, or targets at sea. These are typically multi-mode systems. In other words, they could be operating in one mode when they're looking toward land, and a second mode when the radar antenna is turned and looking out over the ocean. They are inherently mobile, obviously, and they can be deployed to hot spots on short notice. They have been used to basically show the flag at various locations in the world. When the U.S. administration wanted to send a message, they'll make a very public announcement that AWACS planes are going somewhere to make sure everybody knows about it. The whole idea being that you can show the flag with something that doesn't actually carry any missiles. And they can see targets at very long range. They don't have the Earth curvature blind zone problem. We'll see that in a second. And they look downward, so they can see low-altitude airborne threats. They can see vehicles on the ground. They can see maritime targets that otherwise would simply be below the lower beam edges of the ground-based or shipborne long-range radars. This means that it's very difficult to hide from AWACS-type radars. And in that sense, they provide early threat warning for both naval task forces and ground operations. They give you that high top cover that you need to assure you that basically no one's going to sneak up on you from the air. So here we see the classical coverage from the ground stations drawn, as I said, very, very schematically. Now we see the radar antenna mounted on an AWACS aircraft, and I've exaggerated to some extent the downward-looking angle, but my point in this diagram is to show that this aircraft, which is flying through like this, and which has this thing rotating around, being a long-range radar about every 10 seconds, it's sweeping this beam across the Earth's surface like this every 10 seconds while it's flying. And of course, if it wants to, it can get up here and fly a racetrack pattern back and forth. That is, the aircraft can fly a racetrack pattern back and forth. And so it'll fill gaps, and it's looking down, and it's very, as I said, it's very hard to hide from something like this without simply going underground down into a bunker. So that's why these are considered very, very, very important radar systems. Here's the AWACS carried on a Boeing 707 airframe. Here's another type of AWACS carried on a much smaller U.S. Navy aircraft. The Navy planes have to fit on aircraft carriers. These wings fold up, and so they've got some severe size and space constraints and limitations on these radars.
But to refer to those radomes as the Frisbee.
The Frisbee, exactly. And the system is oftentimes referred to Hawkeye. The radars themselves are a whole series of radars that are APS, Airborne Radar Search, and the airframe is the E2C. Newer types of long-range airborne radars that are designed to be mounted on the backs of commercial airframes like 737s are now completely solid-state electronic systems like this. This would be mounted on the back of a 737 airframe, and there are no moving parts. It does all the beam scanning electronically, but the mission is still the same. They just decided, the designers here decided that they liked the trade-offs with building complete solid-state design with no rotating parts, no moving parts. Now this segues into air defense and fire control radars that are used on land and used by naval forces. Basically, in any air defense system, there has to be a search radar capability, which does what the ASRs and the ARSRs do. They have to continually scan around and around, updating every 5 to 10 seconds, give or take, looking for anything out there. And if you need to, you get the airborne systems up so they're looking down. That's fine. Now, having found a target that's of some kind of interest and having ascertained through various methods that it is not a friendly target, you then send queuing information via a data link over to shorter range radar capabilities that can acquire the target and then track the target, and then you can make a decision on what you're going to do about that target, depending upon all the information you have available. My understanding is that the trickiest part about operating these systems is not the technical problems that I've got here, it's the problem of how do you ascertain what you're looking at and how do you ascertain what you want to do about it, because there are certain drawbacks and disadvantages to basically shooting if you shouldn't shoot or not shooting if you should have shot. You can get literally burned either way. But the bottom line is that with long-range search combined with acquisition and track capabilities, you can operate an air defense system. Historically, the search, the acquisition, and track were broken up into separate radar units. Nowadays, a lot of the time, these functions are all combined into one single radar unit that does a lot of electronic switching and multi-mode operation. This is a long-range tactical air defense radar that was used for a system called Hawk. And this rotates mechanically, looks out, I don't know for sure, but I would estimate, just a guess on my part, probably 150 to 200 nautical miles. This would be one of the search radars that I talked about, just one that's used for a defense system. Notice that it's a waveguide running through here, a serpentine waveguide, and it's got slots cut in it. Slot, 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 and so forth. So they're able to do some beam steering using the slotted system on that. This is a naval radar, SPS-48, mainstay of the U.S. fleet. Again, it's got a serpentine waveguide that snakes back and forth here. A huge amount of plumbing built into this array face. Again, it rotates mechanically and steers the beam electronically in elevation. And it has the waveguide here looping in and out along this edge. Those are actual waveguide runs. This is a fully a fully electronically steered radar called the Aegis, also called the Spy-1. That's shipborne radar general purpose or multifunction Model 1. Completely solid state, no moving parts whatsoever. It does use tube technology. It's got a lot of little tubes built into that array face. And on a ship, they'll have 4 of these mounted on the ship, and each one provides a 90-degree coverage. So with 4 of these mounted on the ship, you get 360-degree coverage all the way around the ship. Full 3D coverage, no moving parts, and also nothing, and I'll go back for a second, nothing like this to clutter up your mast. Naval ships often look like basically floating broadcast stations. They have so many antennas mounted up on the masts. So if you can get something like that down to the superstructure, that's a good thing. And then finally, this is a land mobile air defense radar that is bought by the U.S. Army. It's called Patriot. This picture is courtesy of the Raytheon company. This is a radar that can be folded up and moved and then set up again in a very short time period. I would estimate maybe 45 minutes to an hour, maybe maximum. This is only one component of the entire defense system, but this is an example of a multi-mode type of radar. Now, go to the ultimate long-range radar, space search and tracking. These are terrestrial-based radars that are using electronically steered beams to observe things up at Earth orbital altitude. So that's about 90 miles high and above. They look for satellites, they look for space debris, they look for ballistic systems, and they look for re-entry vehicles. They interleave search functions with tracking and path prediction for space objects. Obviously, at long ranges that they operate at, they have low pulse rep rates and long pulse widths. And these radars are used to obtain orbital parameters for satellites, and it turns out that because the Earth is non-spherical, it's an oblate spheroid, and because of perturbations due to the sun and the moon, and because of minute amounts of atmospheric drag, even at orbital altitudes, and also because some satellite vehicles are intentionally and sometimes even unintentionally maneuvered or steered in orbit, it's important to actually update your orbital parameters on satellites rather frequently. So one of the things that is done with space search radars is to regularly come back and look at known satellites as well as looking for any new satellites and space debris and update the orbital parameters for the satellites. These radars are few and far between, but they're very important strategically. This is one, paved pause, again a 10-story building. This is the ground floor, and you can actually see the floors. See, there's the second floor, third, fourth, fifth, sixth, 7, 8, 9, 10. You've got the weight room, the gymnasium, the cafeteria, the daycare center. Not really a daycare center, but actually there might be. It's all inside. When you go to work at this radar, you go into the radar to work. There are 2 array faces angled 120 degrees to each other. This is just one of the 2 array faces. These radars also have a variant which has 3 array faces that's used further north up in northern Greenland and Alaska. These are designated FPS 115/123s, and the V means variant or variable because every single one is hand-built. Every single one differs a bit from its cousins. This is a close-up of the array face. Here you see all the individual crossed dipole elements that are phased to form the beams electronically that this radar is transmitting up into space. Again, in my personal opinion, really an electronic sculpture, an electronic work of art. Now, next is test range and launch support radars. These are radars used at test ranges like, for example, Edwards Air Force Base. If you've ever seen the movie The Right Stuff, you'll see the guys at Patuxent Naval Air Test Center and Edwards Air Force Base. Here, the problem is not to search for a target. Here, they know in advance where the target is one way or the other. They just want to track it for location and for velocity, so they have these parabolic dishes that form pencil beams, not fan beams. Examples are the FPS 6 and the FPS 105. FPS is fixed radar search, and these types of radars are ubiquitous on test ranges. They're also used for launch support. When a launch vehicle is putting a payload up into space, they'll track it with this type of radar as it goes up off the pad and verify that it's basically on course as it's boosting up to orbit. Meteorological, these are weather radars, usually just called MET radars. MET radars are a class unto themselves, and you could spend a lifetime studying them and developing them. The basic thing to remember, I think, about Met radars is that they're not looking for discrete objects, which is what most other radars are looking for. Instead, they're looking for diffuse atmospheric phenomena. They get really, 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 really weak returns off of atmospheric phenomena, and they are looking at very extended phenomena. So, with that said, they don't run search systems with big vertical fan beams. Instead, they use parabolic dishes that form tight beams. I think about 40 to 45 dB of gain on these dishes, believe it or not. Really high gain. And in order to scan a three-dimensional volume of space, they have to scan the beam conically. So the beam starts off, let's say, at a high elevation angle. It makes a 360-degree rotation. Then it drops one pencil beam width and does another 360. Then it drops another pencil beam width and does another 360. So it's a very slow process. But after about 10 minutes, they've scanned a complete 360-degree volume of space. The key to these radars is processing. You know, in real estate, it's location. In Met radars, it's processing. They're continually bringing more powerful processing to bear to see atmospheric phenomena. But with that said, and given that these radars can provide early warning of violent activity, basically tornadoes, tornadoes form so fast that the warnings are always short under any circumstances, and like all radars, the Met radars can miss activity that's brewing up beneath the lower edge of the radar beam, and so tornadoes can and do hit population centers that are below the radar beam, and they can't be seen. So just bear that in mind. Don't put too much reliance into it if you think conditions are right for a tornado. Again, here in red, data processing algorithms are just the key to obtaining and processing Met radar data. They get better and better and better all the time. Here's a Met radar dome. There's a giant parabolic reflector in here. It almost fills the dome, and it rotates, I think, with about actually more like a 15 or 20 second rotation time, and it does this conical beam scanning.
Is this the next rad system?
This is the so-called NEXRAD, N-E-X-R-A-D, Next Generation Radar System. Here we have an ITS engineer and an ITS technician next to the big parabolic antenna inside the dome of a NEXRAD radar.
Those
that gives you
look like-
some sense.
You should refer to them as world-class personnel.
Yeah, world-class personnel. Okay, then, next, maritime search and navigation radars. These are the radars you see spinning on ships, boats, and if a submarine is surfaced and coming into port, in submarines. They're carried down inside the submarine body when the sub is out at sea and submerged, but when the sub is surfaced, it, like ships and boats, needs to have this downward tilted maritime antenna fan beam scanning around, basically updating every 2 or 3 seconds, and it shows you the ocean surface around the vessel. That means you can see other vessels, you can see coastlines, you can see debris in the water, you can see water surface conditions, you can see wave patterns, and I will say, as an editorial remark of my own, not of the NTIA, that I cannot imagine how it is in this day and age that people still hit each other in harbors and at sea, and how anyone can run a ship into a bridge. It's just, it can't happen. If you're using this radar, it can't happen. You've got, something's got to have gone horribly wrong if you still hit a bridge, like in San Francisco Bay, when you because not only do they carry one, but larger vessels always carry at least 2. For most vessels, it's required as a condition of their insurance coverage. So you've always got a redundant backup. Some of these radars operate down around 3,000 megahertz. A lot of them operate up around 8.5 to 10.5. X-band 8.5 to 10.5 is very popular, but you will see them down at 3 gigahertz. Really high pulse rep rates, like 10,000 pulses per second, because they're very short range. They'll operate anywhere from 100 yards or even 50 yards out to maybe 10 miles range. You can set the range as a variable setting on the radar control, and you get an update every 2 to 3 seconds, which is important if you're scooting into a harbor, coming up a channel. You don't want a long time between those radar updates. You want to see what's happening every 2 or 3 seconds. Most of these radars do use magnetrons. They are cheap, they are lightweight, they're very, very rugged. So again, magnetrons of this type of radar are the tube of choice. Here's a slotted array radar antenna. Spins every 2 or 3 seconds. The beam is shaped kind of like this. downward tilted like that. Again, you can see things from a few yards away out to maybe 5 or 10 miles. You have variable range settings. The entire transmitter receiver is a work of art. It's built into this little housing right here. The only thing that goes down from here to the ship's bridge, and this was photographed at a U.S. Coast Guard facility that's on shore, is a video line that carries video data down to a display screen down on the ship's bridge. Other than that, it's what you see is what you get. 2 guys can easily pick this up. It's not very heavy. This is what's inside. See, there's the gear that turns the antenna. There's the whole transmitter receiver unit. Just gorgeous, a work of art. We've had to disassemble these, and I've really come to appreciate the beauty of these little transmitter receive units. Here's a pair of them up on a mast. We were doing some interference testing. We'll talk about this in a later talk in this series. These are dangerous. If they start up and you're standing there, they can kill you if they hit you. Word to the wise on that. If you're ever standing with your head up, it's not the radiation that'll kill you, it's the antenna coming around whacking you in the head.
Both of them on.
That would be bad. That would be bad. Here's one of the big 3,000 megahertz units that would be used up on a big commercial vessel. Again, though, basically, as far as I can recall, this is a slotted array antenna. This is being used for some measurements out in Table Mountain. We turned it into a mobile. And by the way, you can watch air traffic with this thing. We were picking up air traffic over DIA with this because Table Mountain is really high. And all the way out to DIA, which is lower than Table Mountain, this thing, looking out basically horizontally, was seeing aircraft out there at DIA. So these things are amazing units. Wish I could afford one for home use.
Are these affordable for small boat owners?
A small one like this is probably $5,000 to $10,000. So, given what it costs to maintain a boat, otherwise, yes. If you can afford a boat, you can. I would hazard that you could afford this. Here's the smallest, lightest one there is. I won't name the brand, but man, they don't get any smaller and lighter weight than that. Little patch array, really cute. I mean, and it works. You know, it goes inside this housing over here, and again, you put it up on the mast, and the only thing that comes out of it is the video line, and it's got a little magnetron, little bitty magnetron in there, doing all that work. This is what a maritime radar display looks like. A lot of clutter on this display, but they're beautiful. They're beautiful for seeing coastlines, debris in the water, buoys, which are generally equipped with reflectors, etc.
Can you get any Doppler information with those?
Question, can you get Doppler information with them? No.
Okay.
No Doppler. Generally, no. I've never seen one that gave you velocity information at all.
Okay.
Now, however, we now segue into airborne radars, which often do give you Doppler information. These are airborne radars other than the long-range early warning and control. So these are used for a lot of functions: navigation, tracking, fire control, mapping, weather avoidance. Typically, these are multi-mode, but commercial airliners always carry basically a single-function model on board up in the nose, and it is a weather avoidance radar. And I've operated these, and they produce a really nice weather display. These radars, though, unless they're mounted on the side of the aircraft, the way they work is they nod from side to side. If the airplane is moving like this, you're looking at the airplane from above, and the airplane is flying this way. While the radar is flying, the antenna and the beam is nodding back and forth like this. So that's called a sector scan. And sector scanning is popular because the antenna is restricted to side-to-side motion inside the nose. Exceptions are radars that are mounted on the sides of aircraft for mapping or targeting. Unmanned aerial vehicles, now called UASs, unmanned aerial systems, use radars extensively. And I'll give you just a little bit of the flavor. Many years ago, I was flying from Diego Garcia back to Guam. So I was going from the Indian Ocean to Guam, and we had to fly around the coast of Southeast Asia. And it was nighttime. We couldn't see anything at all out there. And we laid these charts out on the navigator's table in the KC-135. We didn't have GPS at this time at all. And even if you did have GPS, here's the problem. If you want to know that you are not infringing upon non-free-flying territory and may be fired upon without warning, consult NOTAMs, etc., you want positive control information that you are absolutely more than a certain distance away from that shoreline. I do not want to rely on GPS for that or anything else. The radar told us. We followed the coast for over an hour, and we saw our exact distance out from the coast. And had we been shot down, I would have been able to testify later that we were outside the range where we weren't supposed to be shot down.
Might not be given the thought.
But yeah, it might not be given. But seriously, it's nice to have that kind of positive control. You really know where you are when you're using an airborne radar for navigation purposes. They're used for search and tracking a lot. Here's the antenna that would be sector scanning like this in the nose while the airplane's flying. Here's the rest of the radar unit built in back here. Obviously, space and weight are at a premium. Therefore, solid state is not a favorite for these. Tubes are smaller and lighter weight and higher performance. And one other thing to note is, given the small size of the antenna and the need for high gain, obviously these radars have to work up in the X band and above, 8.5 gigahertz and above. Another little nose-mounted aircraft radar antenna, same antenna seen from the back. You can see some of the plug-and-chug wiring back in there. Here's the radar unit on a NASA plane with the reflector removed for maintenance. So even at that, even for being, quote, small and lightweight, they're pretty chunky. Here's a side-mounted radar on an aircraft. It's identical to some radars that have been flown on space shuttles, and they fly them on this aircraft looking out from the side of the plane to get ground truth information. And this is a multi-band radar, 400 megahertz, 1200 megahertz, I think 5,000 megahertz frequency bands on this radar. So airborne side looking. So it does everything with electronic beam steering. Now, airborne radio altimeters. Briefly, these are the units that create the emergency warning that says pull up, pull up, pull up, pull up, just before a plane undergoes controlled flight into terrain. CFIT. Controlled flight into terrain means that the pilot was under complete control. He just flew it into the ground. This used to cause a surprisingly large number of air crashes for a variety of reasons. And so these airborne radio altimeters are very simple. They're mounted down in the belly of commercial airliners and also in helicopters, and they monitor the distance from the ground, and they monitor the rate at which the ground is being approached. And if you're too close to the ground and you're approaching the ground too fast, it activates this pull up, pull up, pull up, pull up, pull up alarm. They operate between 42 to 4400 megahertz. Very simple. Precision approach radars, I mentioned these earlier. I won't belabor it now. But they use three separate displays, vertical, horizontal, and range, and they form an X. One radar beam goes up and down like this, looking back from the end of a runway along the glide slope that an aircraft is going to be using to approach the runway. The second radar beam goes side to side like this. And where the two beams cross, that's where the glide slope is, which is an imaginary angled line in space that is running right down to the threshold of the runway, and that's where an airplane wants to be. When a pilot is going to do a so-called ground control approach, the plane is picked up by the PAR, and a controller on the ground talks to the pilot, and the controller says, you're left, you're right, you're up, you're down, and they talk them down to a landing, and that was the breakthrough that they made in the Second World War with PARs. Here's a picture of a PAR. And here you see two separate analog antennas. That's the one that looks vertically up and down. This is the one looking side to side up and down. And operated at 8.5 to 10.5 gigahertz. These are still important types of radars to use in situations where you've got tactical military problems or humanitarian relief missions, where the infrastructure at an airfield for instrument landing system, for example, is either non-existent or has been destroyed. And they can fly these in and set them up pretty quickly. The newer ones don't have the analog antennas. They're all solid state, and they just steer the beam electronically. But it's the same principle. We're almost done. Airport ground control radars called ASDs. These are very much like maritime radars functionally. They prevent catastrophic collisions on the ground. And they help prevent collisions between aircraft on the ground and aircraft that are either landing or taking off on the same runway, where you have a so-called runway conflict. The worst air accidents in history have occurred on fogged-in runways where one plane was on the ground and another plane, for example, was trying to land, and bam-o, they hit it. Ground controllers can use these ASDs, which either look like this, like a maritime radar antenna, or look like this configuration, to watch traffic on the ground and avoid these just terribly, terribly, terribly tragic accidents, which like maritime accidents, nowadays just shouldn't happen anymore, as long as you've got these systems available. Whoop. And I think that was it. And let me just spin down. I may have bobbled the very last slide. Oh yeah, very last slide, sorry. Very last slide, we'll just use it this way. So-called man-portable radars, these are typically used at forward operating bases for artillery spotting. The radar can pick up incoming artillery or missile rounds and back calculate where the round must have come from. And if rules of engagement allow this, return fire can go back automatically and start hitting the location where the artillery came from before the first artillery round actually hits the ground from the opponent. Now, rules of engagement don't always allow that. Because sometimes you want to be more concerned about who you're shooting back at. But bear that in mind, that these are low-power, so-called man-portable. Police radar speed guns, we all know about those. CW signals, they just get speed, nothing else. They operate up around 24 gigahertz. And finally, we have expendable radar types that are throwaway applications in missiles, space vehicles, that kind of thing. Typically, all these are a fraction of a watt to maybe a few watts transmitter power. That concludes the talk.